Yeah, so I'm Remy Lequesne. I'm an associate professor, and I'll be giving the first of 3 talks on what we observed in Turkey following the earthquakes earlier this year. And I do want to point out that the earthquake impacted both southern Turkey and northern Syria. We only had access to the Turkish side, so that will be our focus. So I'll begin with a very brief primer on the earthquakes themselves. On February 6, a pair of large magnitude earthquakes hit with epicenters first in Pazarcik and then in Elbistan, just a few hours apart. And here's a photo, one of our team members in Antakya, and you can see the shaking caused widespread damage. It's pretty dramatic. The impacts were substantial. So considering both the impacts in Turkey and in Syria, there are estimated deaths on the order of 60,000, 3 million people displaced, and I understand many of them are still displaced. And on the Turkish side, economic losses exceeding 1/10 of GDP. So substantial impacts of this the shaking. And I've listed my sources there. So I'll take some time to discuss this slide that maybe some of you can't quite read, but I hope it illustrates a few points. So this is a zoomed-in figure on sort of southeast Turkey, right where it meets the border with Syria. And each of the red dots represents an accelerometer station that was in place. And so we have pretty good information throughout the region about the shaking that occurred. You see they're sort of aligned, roughly linear, and that follows a known fault that did rupture. Each of the plots on the vertical axis shows spectral displacements, and on the horizontal period. These are for linear single degree of freedom systems with 5% damping. The black line is an estimate of what the spectral displacements are for the design basis earthquake. The dashed line is for the maximum considered earthquake, MCE, and then the blue and the red represent recorded, inferred displacements from the recorded accelerations. And you can see throughout this large region, I mean, this is, you say this 200 miles roughly, the range of this, you see shaking intensity was on the order of the design basis earthquake throughout this area. And in some areas exceeded it considerably. In the south, I don't know if I can conjure, south in particular, around Antakya, there were a few accelerometer stations that showed displacements that dramatically exceeded the MCE demand. And so, I guess 2 observations. One, a large area was affected, and second, the shaking was much more intense than expected. And I want to thank our colleague Egman Thonmez, who was part of the team for putting this together. ACI Committee 133, with financial support from ACI and logistical support from ACI, put together a team. And I do want to acknowledge Santiago Pujol and Jonathan Donmez for doing a lot of the organizing on our side of the team, too. We put together a group of dozens of engineers, practitioners, academics, students from all over the world. A large contingent was local from Turkey. We had engineers from ASCE joined us, from NIST, from Wisjani Elsner. I mean, quite a large contingent of folks mobilized. We actually had 2 sort of different groups. This is one of the groups preparing for a survey in Antakya. Over the course of 2 weeks, in late March, early April, so about 2 months after the earthquakes occurred, we spent time visiting 10 cities on the Turkish side and surveyed roughly 300 buildings. And we have complete records for what the data we were looking for about 240 structures. And the way this would work is we would get into buses. We would go to the city of our choice for the day, and we would spend the day, sometimes 2 days, in that particular city, looking at structures. For each of these buildings, we had a group of, say, 3, sometimes 4 engineers that would enter the structure and would primarily focus on what we judged to be the most critical level. Often that's ground level, but in the case of podium structures, maybe we selected a different level. We spent most of our time there documenting damage in all of the vertical elements and beams, etc., anything we could observe. And then also took time to measure span lengths and column wall dimensions throughout that critical level. And so I think some of my colleagues will present more using the data we collected here. But we have pretty detailed data then for 240 or so buildings. The narrative that's come out from these earthquakes, the media has presented, has really focused on problematic detailing. And it's true, that's part of the story, that the shaking, the drifts demands revealed problematic details. And that's the focus of my talk. I think there's more to the story, so I hope you'll stick around for the other 2 talks this morning. Yeah, there were a number of problematic details that we saw over and over again. And I'm in no position to explain why they were there, but they were there. So concrete cover was often inadequate. Spacing of bars, especially where the bars were spliced, was often inadequate. You can see a photo on the left there. It's effectively a wall of reinforcement with not a whole lot of space in between bars. Also, pretty pervasive lack of cross ties where I would have liked to see them. And I should note, these details are not compliant with the Turkish code requirements either. It's not the deficient code necessarily. We saw a lack of 135-degree hooks in all kinds of elements. As a column that did not perform well. We saw widely spaced transverse reinforcement around small diameter longitudinal bars. And I think that's sort of an interesting note. The spacing here may be okay if the bars were number 8 or number 9. These were roughly number 6 bars. And I think they prefer to use these smaller bars to make it easier to bend in the field and place. But then that, of course, makes buckling more critical. We saw several examples, this is very common, having buckled bars right around the perimeter of the building at the top of the foundation. And so in this case, there was a column that appeared to have good confinement throughout the clear span and confinement in the foundation. But at the joint between the foundation and the column, the space between the bottommost column hoop and the topmost foundation hoop was too wide. And of course, the bars buckled there. You saw a lot of these. I don't know if you can see what I'm looking at here. This is a zoomed in photo of a column. And so I'm sort of tracing what would have been the base outline of the column section where it met the foundation. And if you can see this bar coming out of the foundation that was bent into sort of a dog leg to fit into where the hoops and the column cage were. So it wasn't quite lined up properly. These dogleg details effectively function as a pre-buckled bar. As soon as you start to displace, they want to straighten and then bend. And we saw several examples where this detail led to bar fractures. We do have offset bent longitudinal bars in our code, but there's a requirement on angle. In many cases, these were much steeper than the permitted angle. There were a lot of lap-spliced bars where it's convenient, so at the base of columns and at the base of walls, and that caused all kinds of concentration of damage. So this is a photo of a column with a lap splice within the span right above the foundation. That leads to a stiffer section right above the foundation. Rotations concentrate at the joint with the foundation, and in this case, buckled the bars. So in this case, the splices survived, but caused a localization of damage. And this is actually quite a scary building. The columns had effectively slid off the foundation in some locations. We saw this in walls, too. This was a 3-meter long wall with lap splices that began about 70 centimeters above the base. And so, because then you have a stiff section that's, well, starting 70 centimeters above the base, even if the splices do well, you have pretty localized damage at the base of the wall. So you don't get the distribution of damage you might hope for. Another example of a wall with lap splices, this time at the base of the wall, which was permitted until 31819. I'll note that. This is a detail we would see all over. In this case, the stiffer section at the base caused damage to localize right at the top of the lap splice. Right? You don't even have to be able to see the lap splice to know where it terminated. And then those concentrated rotations led to eventually spalling and failure of the lap splices. I don't think I have a photo of it, but the lap splice here effectively has no concrete left in that boundary element. So this wall was badly damaged. I think it's fair to say I think it's a good thing we don't allow lap splices in these areas anymore. This is an issue I didn't expect to see, but we saw it frequently in beams with longitudinal bars, on the bottom face that were terminated, say, 3 member depths away from the face of the column. And so we had 2 continuous bars and 3 terminated bars, and instead of getting, rotations at the face of the column where I'm sure the engineer was hoping to see them, we saw concentrated rotations right at the bar termination location. And in this case, that was made worse by the lack of closely spaced hoops, and so the continuous bars buckled and fractured. So I thought is warranted about where to cut bars off in beams that are going to be experiencing large rotations. This is a photo of a beam, a short, deep beam that behaved like a coupling beam, but judging by the reinforcement that was provided, was not intended to operate as a coupling beam. There's no inclined diagonal bars. We have pretty light longitudinal reinforcement and hoops, or probably stirrups, at less than d over 2. But the damage was extensive, right? This is badly damaged. And even if it wasn't essential for the lateral performance of the building, this is fall hazard. This can cause a danger to the folks living in the building, and it also leads folks to not trust the building. And so we heard about demolition decisions being made based on damage like this. And so if we want folks to feel comfortable living in structures, remaining in place, we need to think about limiting damage like this, even in non-participating parts of our system. And I use that in quotes, non-participating, everything participates, whether we mean it to or whether we mean it or not. There are a couple more details that I found interesting. This is a photo of a relatively well-confined column near the corner of a foundation. I don't know if it was well-confined, but it was confined better than the bars in the foundation. So if you're going to get yielding at the base of a column, that yielding will extend into the clear span, but it will also extend into the foundation. And if your column is located near an edge, those bars need to be restrained against buckling. And we saw this detail, this problem several times. I mean, you can see here through a roughly meter deep foundation element, there are no hoops. And it's a life safety problem. This is a photo of a column with a similar issue. The bars in the foundation were not confined. They buckled, and so this relatively slender column slid off the foundation And I don't know if you can see with the way the photo is cropped, but the beam above this column is sagging appreciably. So we did not feel safe entering this building. I took the photo and kept walking. But that is a life safety hazard. And so I was interested to note that ACI prohibits this detail, or more accurately, requires confinement in the foundation near edges if you're building in seismic design categories D, E, and F. But we don't require it, as far as I can tell, in intermediate moment frames. So that would be something I'd suggest we consider looking at. Another detail that I thought was interesting, we saw several examples of unconfined beam bars passing through beam column joints. You have the column cage, column core. This joint also suffered from a lack of transverse reinforcement in the joint. But the top and bottom beam reinforcement on the outside edge of the beam passed outside of the core and was therefore unconfined throughout the whole length of the joint. We saw this in interior joints, saw this in an exterior joint. This is actually a relatively well confined joint. I would like to see 135-degree bends, but there was transverse reinforcement. I don't know if you can see it. There were 5 column longitudinal bars, and the hook passes outside the first 3 and then gets tucked inside, thankfully. The tail is inside the core. This is a beam framing into a relatively long or large column, and so the bars weren't even hooked. The outermost layer, or the outermost bars, were just developed straight into the column. And, of course, they broke out. As soon as damage started to occur in the joint, they broke out. We actually, on this site, spoke with the contractor who was building this building when the earthquake occurred. He said the inspectors actually prefer this detail because to get the bars inside the column core, you would have to move them further away from the outside face of the beam, and so you'd have excessive cover. And so inspectors preferred to have them on the outside to limit the cover. This is a problem. Excessive cover is not. And so I think it's interesting that we require confining those bars that pass outside the joint for special moment frames, but I would, and I will tomorrow actually, suggest that 318J consider requiring this for, well, what I'll call non-participating frames, intermediate moment frames, and ordinary moment frames. Those bars have a lot of demands on them, and I think they ought to be confined. I have just a couple more slides, and then I'll get to our recommendations and et cetera. But I do want to highlight the role of non-structural damage in the impacts that we observed. So this is a photo of a building that performed well, roughly speaking. The frame, the wall elements were relatively lightly damaged. It was located in Antakya, but you can see the damage to non-structural elements was extensive. And that is a safety hazard. If there's debris like this falling, that's dangerous. And it makes the building totally unusable. And even if it could be repaired easily, and I'm not sure this case could, when you have widespread damage like this, you don't have materials to make these repairs. And so if we want to limit displacement of folks, we need to limit non-structural damage. We're not the first to observe that. Lastly, I want to highlight damage to reinforced concrete stairs. We saw this frequently in buildings. They used reinforced concrete stairs that were fixed to the slab at the lower level and the upper level, and then apparently not detailed to accommodate that interstory drift. And so you have the landing with some flexing demands, and the concrete breaks out quite quickly. And this is dangerous, right? This is an egress path for folks, and so we ought to have better details for our stairs. So with that, I'll summarize briefly, and then thank you. The first observation is that the large drifts that were there revealed problematic details, many of which were not code compliant. I do think that what we saw suggests ACI 318 might consider a couple changes. First, requiring confinement of column and wall boundary element bars in the foundation near edges. For intermediate moment, intermediate mortar frames, and then requiring confinement of beam longitudinal bars passing outside the column core in cases other than special moment frames. And then, of course, detailing non-structural elements is important. So with that, I'll thank you. I don't know if I have time for a couple questions.
Yeah,
but.
Go ahead. If there's some questions, feel free to come up and talk.
Look at the impact of the interface.
Can you read, just so everybody in the back can hear you?
So I think these are frames that have infill walls in them, right? So what was the impact of the infill walls on the behavior that you saw?
Okay, I guess they can go a couple different directions. So, first, the infill walls were not detailed to be connected to the frames, and so it appears that they broke out and became unstable relatively quickly. They do, of course, especially if there are no openings, if they're confined by a frame, they do add some stiffness to the system. I think in the talk that Santiago will give, he'll consider the effects of walls and, to some extent, masonry walls. I think there are examples where that has been beneficial, but I don't know that we saw clear examples of that in Turkey.
Remy, thank you for the good presentation. I appreciate the details. Since I'm originally from that region, part of the country, not Turkey, but on the other side of the border in Iraq, these kind of deficiencies that you talked about, I can see that, these are very prevalent in our construction as well. One type of construction that's really common in this part of the world is that wind tunnel construction. And I would like, I don't know, maybe Santiago would chime on this one, but I would like to know what was the performance of these types of buildings. And I understand these are really poorly detailed, but the good thing about them is just there's a lot of walls, and typically they have, lower displacement and things like that. I don't know if you have observed any damage in these type of buildings and any observations.
I'll give you a brief answer, and I think Santiago will touch on this, and Changwu too. We did seek out, it's a great question, we did seek out tunnel form construction. So these are buildings where they have relatively few columns because effectively every wall that can be reinforced concrete is reinforced concrete. In some cases, the tunnels are all sort of oriented in one axis, so you get a lot of walls in one direction and few in the other. That is good in one direction and not so much in the other. But we did see some buildings with a lot of walls in both directions, and they did dramatically better. So I hope I didn't take the punchline away, but it's a much better detail.